So, good afternoon, everybody. This is the last speaker of the lecture series of the Italian chapter of the System and Cybernetic Society for the first semester. Then we'll start another series starting on September. So you know everything about IEEE and the society, System and Cybernetic Society, as the three pillars: systems, human, and cybernetics. And there will be a conference. The main conference will be this year in October in Hawaii. And this is the lecture series I organized. And as I was saying, for the first group of series, Bruno is the last speaker. Next July, there will be a conference in Turin, and there will be the first System and Cybernetic Italy chapter day will be on July 7 in Turin. And so the next speaker today will be Bruno Sinopoli. He's coming from Washington University, and he will give us a talk about modeling, analysis, and design of influence in multi-agent systems. Bruno got his PhD from Padua. He's a laureate degree from Padua and his PhD from University of California, Berkeley. And then he joined he was faculty member at Carnegie Mellon University. And in 2019, he joined the Washington University in St. Louis, where he's the director of the Center of a Cyber Physical System, and is also the chair of the Department of the Electrical and System Engineering Department. We all know his research, but for the one that doesn't know him, he had a lot of work on cyber physical systems, smart systems, smart infrastructure systems, and is trying also to understand the connection between machine learning and human learning. So please, thank you, Bruno, for giving us this talk, and you can share your screen.
All right, wonderful. First of all, thank you. Let me share my screen. Update, no. Screen. Oh, you see my screen, good. And as you can tell, I'm not very accustomed to Teams, but here it is. Can you all see the slides?
Yes,
and,
yes.
And
yes.
If you cannot hear me, please let me know.
Yes.
So it's a great pleasure to be here. I want to thank, of course, Laura for inviting me, and Italian chapter of the Society for hosting this great event. I think it is a wonderful event, and I'm really, really happy to be here. Before I get started, there are two things, right? If you wonder about Washington University in St. Louis, as an Italian, there's two reasons. Actually, as an Italian, there's one main reason why you should remember this university. This is a university where one of our most famous Nobel Prize spent 40 years. That's Rita Levi-Montalcini. She was at WashU from 1937 to 1977. And as a control people, there's another good reason, is that Alberto Isidori was a professor in the department that I'm heading now for a few years. Okay, so with that said, today I'm going to trying to talk a little bit about the problem that is that I've been interested in for now a few years, which is the one of characterizing mechanisms of influence in multi-agent systems. This is work that I started when I was still at Carnegie Mellon, and as a matter of fact, it's joint work with my former colleague Shomokar and with my current students who just received their PhD in May, Carmel Fisco, and I owe her. I mean, most of the work that I'm going to present, it's really her work. She's currently on the market for a postdoc, and if you're interested, please let me know. So, what is this influence in networks? This is something that we have been observing in several contexts, in particular in social networks. Basically, describes the special agent in a network that have a special connection to a very large number of users or agents, and this agent is able in several ways to influence the decisions of the other agents, right? And you can see influencing prices, for instance, of currencies, like Elon Musk did with Dogecoin. And there is a lot of history of injecting misinformation in social network so as to induce people into believing certain things or into voting a certain way. Anyway, it has become a very powerful tool. And therefore, I think it's really worth studying, right? It can be used for all sorts of benign reasons as well. For instance, a text message saying that by the California Power Authority saying that we are running out of power, please decrease your consumption, was able to induce people to conserve and avert one of the major blackouts, what would have been one of the major blackouts in 10 years. So the issue is, right, the problem is quite clear, and I think and I hope that you are convinced, like I am, that it is an interesting problem. But how do you approach this problem? I think in this case, modeling in particular is key to being able to say something about this problem. You can build sophisticated models that are very descriptive, but what we're looking for is really a prescriptive model. Right? So something that allows us to do design and analysis in a scalable way. So what are the elements? There are intelligent agents who make decisions in a certain environment. It could be social media, economic networks, cyber physical systems, and the likes. And there's a group behavior which results from this individual decision-making process by each agent. So in order to achieve global control objectives, policymakers must understand how people, what drives people's decisions, and understand therefore their relationships. Okay, but the main questions that we want to answer is how we set up this inference problem, and how does a central planner choose to act in order to achieve its goal. Right? And again, as I said just a minute ago, we would like to develop not just a model that describes this phenomenon, but we want a model where we can do analysis to draw provable guarantees. It's a model that is scalable, given in many cases large size of these multi-agent systems, and a model that is amenable to efficient computation, so that even if we develop a solution, we can actually compute this solution. Okay, so these are our guiding principles. So here's what I'm going to talk about. First of all, we'll talk about the modeling of the influence systems, and we'll model it as a Markov decision process. We'll talk about then policies which are cluster-based. So we try to provide different incentives or different influence signals to cluster of agents. Right? and see how much better we can do rather than sending just one single influence signal to everyone. And then we'll look at the issue of robustness, in particular this issue of robustness to impactful agents. So we want to make sure, we want to see what happens when an agent changes its behavior, how it affects the overall policy. And given that many of these networks are very much dynamic, how to be robust to no dropout. Okay. So here, just a short summary of Markov decision processes. Right? Markov decision process is a tuple where there are states S, actions A, and a single stage reward, which is a mapping between the set of states and agents into R, and then a transition, which are Markovian transition, and then a discount factor, which of course belongs in the 0-1 open interval. The Markov assumptions holds, so the probability at the state is t plus 1, given all the past, is the same as looking at the last at the previous step. And what results out of this Markov decision process is a trajectory, which is a triple of states, actions, and rewards. Okay, how do you solve for a policy? You want to find a policy that maximizes the discounted cumulative reward, and you can use the dynamic programming, the usual value function, which is shown in the slides. Okay, the solution techniques depend on your information set available. Right, it can be either model based, and then you can use value iteration or policy iteration. Or it could be model-free. We don't know the transition probabilities. And then you have to resort to model learning approaches such as Monte Carlo, Q-learning, and others. So let's try to model the system as an MDP. So we have N agents, intelligent entities, right? And each agent N has a substate, Sn, in Sn, where a substate of the overall state, which is just the cross product of all the states, and it will call the overall state S. Could also consider a tuple of Sn and An of substate and action agent, which is usually the standard in multi-agent reinforcement and learning. The trajectories contain a sequence of states, which is generated by the agent's decisions. And the agents define Markovian agent policies to make decisions that accomplishes their objectives, right? To the right, you see two examples where you have only actions, right? Which is something that occurs often in game theory, or where you have a pair of states and actions, where you choose an action to get to a certain state. Okay, there's a ton of work in depending on how you set up the problem and other type of influence mechanisms, right? But just at a very coarse level, we have game theoretic approaches that go all the way back to John Nash, to multi-agent reinforcement learning, which has become very, very popular in the last few years, and distributed optimization techniques, consensus, and unfederated learning. Where the last are not really considered system dynamics. It's usually just solving an optimization problem, just one shot objective. It doesn't look at long-term horizon. Okay. Let me give you just an example. Right. Let's say that you have a game theoretic example where you have two agents that take actions, all right, 1 and 1. And if you use best response dynamics, then you can characterize your game. And you see that there is one Nash equilibrium at action one for both players. Okay, I'm going to get back to this example. So let's introduce the notion of a, I'll call it influencer, I'll call it central planner, and it's basically a it's a global influencer that selects a potentially n, one for each agent, signals to exert influence, to encourage the agents to reach a certain desired global group behavior. Okay, so the policy of the central planners is alpha t. Okay, we'll assign also reward with this central planner, which is usually designed to induce behavior. We'll assume that this is finite and deterministic. Let's say, for example, that the central planner is interested in the agent to reach a certain subset, let's call it D, of the state space. What you can do, a very natural definition for a reward for a central player, is to define the reward as the indicator function for that set. Right. So basically, you get a reward if the state belongs to that subset of the to the set of desired states, and zero otherwise. Okay, everything is clear. If it's not, please don't type because I don't see anything. Just speak and ask your question. Okay, and feel free to stop me at any time rather than waiting until the end. Okay, so the MDP transitions that arise from these agent policies, right? So we assume that each agent has converged to a stationary policy and then observes this influencing signal, right? Then what is the probability that the state will be at S prime, given that the previous state is S, and given that the influencing signal is alpha. Okay, so we'll make some assumptions, right? For instance, the decision policy of each agent is time homogeneous and satisfies the following assumptions. Okay, in other words, what we're going to say is that agents have learned their policies, and the super player or central planner exploits this fact, and as a result, the transition matrix can be factored as the product of the transitions for each single agent, right? And as a result, we have a factored MDP, which is key for our subsequent analysis. Okay, let's go back to the example of game theory. Okay, let's assume, right? If you remember, the previous example was with alpha equal to 0, right? And if alpha equal to 0, then the state that eventually the game reaches is S1, where both players choose action 1. Now, let's say that a central planner can toggle this parameter alpha from 0 to 1. And that results in a different gameplay. And for instance, if you choose alpha equal to 1, then you get a very, very different dynamics where now it induces a different gameplay where the Nash equilibrium is now S3. Okay, just as an example. So so the first question is, right, if the super player or this central planner has this control knob, which we call alpha, And at the moment, let's assume that alpha is a scalar. That means that the central planner has only one control knob that needs to apply to all the agents. Okay? The very same one. Can we characterize what we call reachability? Right? Given alpha and given the set of actions or the set of values that this alpha can take, we can define this notion of reachability. And we'll say that a state J is alpha reachable from I if there exists a sequence of alpha and some t such that the probability that you reach J at ST by starting at I through a sequence of actions is non-zero. Okay, and this is general. You can do it for vector alpha. It doesn't matter. Okay? Now let the matrix R be defined in this form. Basically, you can easily check whether a certain state is reachable because the state J is reachable from state I, and you check just the IJ entry of R, just a matrix, and if this is non-zero, then that state is reachable. Okay, so reachability can be defined in a very natural way and can be checked very easily. Okay. Now, once you have defined this notion of reachability, what you would like to do is see whether how to design a policy, a sequence of alphas, so that you can actually achieve your objectives, right? And you can find the optimal policy by maximizing the you want to find the policy that maximizes the cumulative discounted reward. So the theorem states that if you have a set of desirable states D, and this set is reachable, right? And the MDP, as I described above, as an indicator reward function, the one says that you receive a reward if the state is in D and zero otherwise. Then for any optimal policy, there exists almost surely a finite time tau such that the state will be in D at time tau. Okay, so basically this theorem tells you that the optimal policy will reach with almost surely will allow the state to be in D. Now, if it reaches a Nash equilibrium, it will stay there indefinitely. If not, then it will keep oscillating probably, right? It will return an infinite amount of time into D. Okay, so the two main contributions here are, we could assess the reachability of control objectives without having to solve the MDP. And then we prove that the existence of policies that achieve the reachable control objective, again, for indicator reward function, and the main assumption is underlying that the policies are Rockovian. Okay, all right. So if we go back to our very, very simple and trivial academic example, okay, perhaps if you have a question, say it. If not, maybe you can just mute so as not to bother the audience. We have two equilibria, right? S1 and S3, depending on whether the super player chooses alpha to be 0 or alpha to be 1. And the question is, are S2 and S4, for instance, reachable? And you will see, if you compute the matrix R that I showed you before, you'll see that S2 is not reachable from any state, and you can confirm with the graph, which is easy in this case because the network is so small, right? And while S1 and S3 and S4 are reachable from any initialization. And you'll see the values of V for S1 and S3 being high because these are the equilibrium. Okay, so far, and as you have seen in that example, we used alpha as a scalar. So the central planner or the influencer just sends one single signal to all of the agents. You might understand that this is that an agent was able to send more personalized influence signals to different agents could achieve a behavior which is at least not worse than before. You can do only better, right? So this is just a depiction of it. Let's say in a traffic example that you want to, in the first case, you try to influence all the agents, whether they are pedestrians, motorcyclists, cyclists, or drivers in the same way. But of course, in many general applications, you would like to distinguish between different types of agents and send a signal which is tailored to the type of agents. Okay. So, and let's say that so this results in cluster-based control, right? Where you have your MDP, where you have C clusters, right? And now the transition depends upon the influencing signal, which is now a tuple of it's a vector, not anymore a scalar. So so as I said before, if you have C disjoint clusters, then you can only do better, right? And this is clear to everyone, right? It's a very simple proof. The problem with it is that as you send personalized signals, complexities in finding the complexity of finding the optimal policy increases exponentially with the number of clusters, both for policy iteration and for value iteration, because the decision space increases exponentially with it. So what we would like to do is find a efficient cluster control policy without having to explore exponentially all the possible options. Okay. So let's look at approximate solutions. Instead of solving for the Bellman operator, so maximizing over all the different clusters at one, as you see in the equation above, we modify the Bellman operator, by calling this cluster Bellman operator, where you basically maximize over one cluster at a time and in a round robin fashion, right? So you optimize over a cluster and then you move to the next cluster. Clearly, this policy is suboptimal because the optimal thing to do would be to do it all at once, right? But the benefit of it is that the complexity for iteration, for this cluster value iteration, decreases because you basically you eliminate the exponential dependence on the number of clusters. Okay, everything clear? So hard to get feedback from the audience when you're doing these things online, but if not, please let me know. Okay, so what are the main results, right? So we have an approximate solution that you can say we pulled out of the hat, right? So what we need to do is evaluate, right? How good is this cluster value iteration? So the next couple of results will do exactly that. First of all, convergence. First, we can prove that the cluster value iteration converges to a policy. which we'll call, so the value converges to v hat, and the policies converge to policies, which is p hat of x. Right? Now, how good is this approximate solution, and how far is it from the optimal solution, the one that would be that you would get if you solve the centralized or the overall problem all at once, which we call V star. We'll say that the gap, so the following theorem establishes upper and lower bound for the optimality gap, and it is shown as above. Of course, we cannot say how tight these gaps are. In order to do that, we did some extensive simulation that I will show in a moment. Before I do that, I want to talk about a very specific case, which is the case of separable MDPs. Separable MDPs is where the reward is separable per cluster. So the overall reward is the sum of the reward over each cluster. Right? If you have separable MDPs, you can the value function can also be separated. And if you're in this case, again, which is a very special case, you can prove that the cluster value iteration on separable transition-independent MDPs will converge to the actual true optimal. In other words, for separable MDPs, the cluster value iteration will yield the optimal policy and the true optimal value. Okay. So if you have this structure, then you can use it in order to improve the efficiency of the technique. So if not, then again we have these bounds, right? But we don't know how tight these bounds are. So we conducted some simulations where we have 7 clusters, right? And in the figure to the left, no, actually you have n agents, and sorry, 7 agents, and what you will see is the the bars will give you the optimal solution as computed with the regular Bellman operator. The black dot, which refers to the y-axis on the left, which is the values, right, will show you this optimality gap, right? And you will see that actually the cluster value iteration approximates pretty well the policy under the cluster value iteration. Actually is pretty good because it's just slightly suboptimal, right? And also it almost always achieves the upper bound, which is given by the error bar in black. Okay. What you will also see is that by using more and more clusters, you achieve a better value, right? The yellow part of the bar refers to the case where you have only one cluster, right? And the blue shows the improvement of using more and more clusters, which confirms what we had in the theorem, is that by adding cluster, you do actually better. Right? This is one of the most important slides in the talk. So if there are things that are not clear, because it's a very rich one, please interrupt and let me know. If you look at the y-axis on the right, then we look a little bit at the savings in terms of computation time, right? And you will see that the time of computing the regular value iteration can get up to 1,000 times longer than computing the cluster value iteration, which you will see with the red, it's the red dots. Okay, so the takeaway from the last slide is that by using cluster value iteration, you can approximate well the optimal value, which means that the policies that you find through cluster value iterations are almost optimal, and you save a lot of time, right? Computation time, which in this case, right, if the number of agents, number of clusters is large, then at some point, actually computing the real value iteration will be infeasible. So not only you do better, but actually you will be able to compute a policy in the cases where the problem explodes for the regular algorithm. On the graph to the right instead shows what we proved in the theorem, which is the separable case, right? And you will see that here that the value for the cluster value iteration, which is again showed by the black dot, sits on top of the value of the regular value iteration, right? So there's no optimality gap. And so you do optimally, and you still save the same amount of time. Okay, questions? All right. Now, here we assume that the clusters are given, right, which is a big assumption. So how would we go about then choosing a clustering assignment? Okay, the question is, which is the optimal clustering, the clustering that maximizes the values, the value of the value function, V star. Subject to, right, that the agents are assigned to this joint cluster. An agent cannot be into clusters, right? As you can see, this is a classic NP-hard combinatorial problem, right? You can bring it to show equivalence to a set covering problem, right? And right, and checking all the combination explodes in a combinatorial way, right? For instance, if you have 8 agents that you want to put in 5 clusters, you have already more than 1,700 1,700 combination, right? So again, just in the spirit of our approach, we want to provide proxy methods that are easy to compute and give good enough value. What comes to rescue us is the notion of submodularity. Some of you, especially those of you who do optimization, know already what a submodular function is, but basically says that by adding elements to a set provides diminishing returns, right? As you can see in the definition, right? If you have the sets X and Y, and X is contained into Y, if you have Z, which is not in Y, if you add the Z to X and subtract to X and compute F over X union Z, and you take the difference, is greater than if you did the same thing over Y, right? And this is the notion of diminishing returns. Okay, how do we exploit the submodular function, right? If we have factor MDPs with some modular rewards function, have also a reward function, have also some modular value functions. Okay, and what are these submodular reward function? Is this agent separable rewards, to the same assumptions that we had before for our cluster value iteration. Okay. In other words, if you are in this if you have this agent separable rewards, you have some modular rewards. Therefore, you have some modular value function, which means that if you add an agent to the system, the marginal improvement to the value function decreases. Okay. And so, with this in mind, we want to propose an approximate clustering scheme, analyze its performance by exploiting some modularity. Okay. So the clustering that we propose is called greedy splitting. But basically, at iteration k+1, you want to choose the clustering assignment there is the best refinement of the existing K clusters. Okay. Theorem says that in terms of performance, that for MDP with some modular rewards, and I understand this, you might say these are a restrictive assumption; they only apply to certain type of multi-agent system. The sequence of clustering found by this greedy cluster produces the following value, which basically this modularity property kicks in, which says that by adding more and more clusters, you get these diminishing returns, right? So the difference between the value between k plus 1 and k is less than the difference at the previous step, right? Which is exactly saying that by adding another cluster provides an improvement which is less than the improvement that we reached at the previous step. Okay, let me show you this in simulation, right? And let's say that we have up to 10 clusters, right? And so what you see here is, first of all, in the purple bars, you see this some modularity property in action, right? Where you get big gains by clustering at the beginning, and then the gains decrease, such that virtually after using from 5 cluster and onward, basically you get very, very marginal improvements. Okay. And in other words, but on the other hand, if you look at the black dots, which are shown, whose values are shown on the right-hand side of the y-axis, right? That you will check up to 1,000 less clusters, right? And which happens in the middle, and which is the place where you have most combination. Okay, so basically, what just to summarize, by using this greedy splitting, you reduce the search space for clustering assignments, right? Of course, you don't get a lot of gains. You don't get when you use all the clusters, because right where you cluster all the agents, where you use one cluster per agent, right? And at the beginning, so you get most of the gains there in the middle. Right? You get this guaranteed monotonic and some modular improvement in value. And you get lower bounds of optimal values for the optimal clusters, right? It's really tight at the endpoints, right? And that's it. Okay, do you have any question on this? So let's go back to our content. So the first part was modeling. The second, we looked for policies that are suboptimal, but have some notion of suboptimality, and they can be efficiently computed. And I hope that I convinced you that the proposed clustering method and the cluster value iteration are actually pretty good approximate solutions for the general problem. The last part, and I know I'm running out of time, so I will go pretty fast, is the notion of robustness. Right? We'll look at robustness in two cases. To impactful agent, let's say there is an agent that misbehaves, right? Let's say that we have devised a optimal, we as a central planner has devised an optimal policy, knowing all the policies of all the agents, stationary policy of all the agents. Now, at some point, one of the agents just changes its policy, right? So we want to know how the optimal values or the values decreases, right, as a consequence an agent not behaving in the predicted way, right? And this is a way also to highlight what are the most important and impactful agents in a network, meaning the agents that can decrease the value or the reward for the central planner the most. Okay. The second is robustness to node dropout. What happens if you have devised a policy for a certain network and one of the nodes disappears from the multi-agent? How optimal is the policy that was designed before, and how can you design policies that are robust to node dropout? Okay, so let's look at the first case, right? So the first case, basically you have a new behavior, right? You have an agent that changes behavior, adopts a new policy. The second case, you have a permanent or semi-permanent, make this probabilistic, removal of agent from the system, right? This is the case where a company goes out of business, a user deactivates an account, or physical infrastructure, for instance, is damaged, right? Whether you are in economics, in social networks, or in cyber physical systems, right? Now, the question is, can you find a policy pi provides good value for both the pre-change and the post-change systems, right? If I am a central planner, I might want to devise a single policy that does not penalize me in the case where the system behaves just normally, but also does not drop dramatically when one of these disruptions occur. Okay, so let's take a look at the case of where an agent changes his behavior, right? And pretend, right, in a worst case scenario, that the agent of interest, which we'll call N tilde, is an adversary, intelligent and malicious, right? So not only changes its behavior, but wants to change its behavior in such a way that minimizes the value function for the central planner. It wants to change its behavior so as to hurt the central planner as much as possible, which can be formalized mathematically, right? The impact is V star is the optimal value for the central planner. Yeah, you subtract the min max, which is so it's the impact of this adversary agents, right? So given this approach, right, we can define the central planner strategic form games with players, with two players, right? The central planner, which has action space A, mixed strategy pi, and utility function Q phi pi SA, and the adversary, which has action space Sn, right? Only can control only his actions and its state, right? And mixed strategy phi, and a utility, as you see in the slides, right? You can conclude very easily, right, that when you see this min max, that this game is a zero-sum game, where basically the Q function for the adversary is just the negative of the one for the central planner, right? And in this particular setting, it is known that there exists a Nash equilibrium solution to G. Okay, and this Nash equilibrium is equal to the mean over phi n, max over pi of v pi phi n, right? The min max solution. Why is this useful, right? And this is just an example where you have four agents, right? And on the first row, you will see the impact that the agent has on the overall value of the value function, right? And you will see that if the central planner does not account for the possibility of an agent misbehaving, you will see that agent 1 and agent 3 can both cause a dramatic decrease in the value of the central planner. So they can are very important agents, right? They can really disrupt the operation of the central planner. But if you design your policy in such a way as to minimize the maximum disruptive effect of all the agents, you will see that that basically you can temper the effect of agent one, right? And sorry, of right, and actually of agent, yes, and while agent 3 is not. So in other words, in other words, this is a way to characterize what agents are important in the network, in the sense which are the agents that can be most disruptive, even to the robust behavior, right? And here, sorry, you can see in the second row that that basically by using the robust policy, the agent 3 is not disruptive anymore, and the only agent which is disruptive is this agent 1, which still can decrease even under the robust policy the value by 27%. And why I think that this new notion of is important is because if you look at the usual notion of node centrality in networks, none of those, the degree centrality, betweenness centrality, closeness, and the likes, can identify, in this case, which one is the most important, node, because they're all based on the notion of connectedness. And since in this example we have a fully connected graph, then all the nodes look the same for all these other notions of centrality. Okay, all right. So this is some of the current work that is ongoing, and let me just spend a minute on agent dropout. So consider a system M, right, made of 4 agents, right? And consider the case where any of the 4 agents can drop at any given time, right? So how do we find policies that are robust to any agent dropout, right? Now, if you have the model for the system, then and you're able to characterize which agent has dropped, then you just solve the problem on the remaining network, right? The problem arises when in the model free case, when actually you don't have a you have to design a pre-dropout policy that takes into account, which is robust to dropout of nodes, but you don't have a model. Therefore, you don't have the luxury to observe what will happen to the multi-agent system after the dropout exists, right? In this case, under certain assumption, you can use policy importance sampling in order to derive a pre-dropout policy which is robust to node dropouts, right? I'm going to not go into the details in the interest of time, but I will put some of the references at the end. Let me just go to conclusion, right? So what we try to do here is characterize the capabilities of a central planner, of an influencer in a multi-agent systems, right? So what we showed is we characterize this notion of reachability, right? Which basically says that when the central planner can move the equilibrium of this multi-agent system, right? And they can either reach an equilibrium or realize a better group behavior. What we like about this Markov decision process formulation, rather when compared to game theoretic approach, for instance, is that this is amenable to using all the new techniques in reinforcement and learning. So we found some insights for general reinforcement learning beyond the multi-agent system, right? Reachability, cluster policies, and robust design. And what we are doing now, we are dropping the assumption of knowing the model, knowing these transition probabilities, right? And looking at active learning schemes, where the central planner has to use its action not only to achieve optimal group behavior, but also to learn the system. And there you fall into this category of explore, exploit, right? Which is the basics for multi-arm bandits and reinforcement learning. Okay, so these are some of the references of not to our work, but general references. And with this, I would like to conclude. And I want to thank you for your attention. I'll be happy to answer your questions. And if there are students, PhD students, who are here in the audience and are interested in this kind of problems, please send me a note. I think here we only scratched the surface. There's if you start looking at what we did and looking at the problems, there's a very large number of directions when this work where this work can be taken. So I'm looking forward to discussing some of these directions with you. All right, thanks.
Yes, there is a question, but what we do usually is we stop the recording so that people feel free to ask questions without